We're very excited to welcome you to the ELSC seminar series this year. I'm Aya Ben Yaakov, and this is Jonathan Kudman, and we're organizing the seminar. We're no faculty here at ELSC. This year, the seminars are going to be partly frontal in-person meetings because we hope to kind of regain some of the sense of community that we lost. Everyone kind of lost during COVID, so we strongly encourage everyone to attend these meetings and to come to the happy hour after. And on the other hand, Zoom gives us the great opportunity to invite great speakers like Viola. So part of some of the talks will be in Zoom, and I'll hand it over to you.
Okay, thank you, Aya. So for our first talk, we're very happy to have Viola Priesemann from Göttingen. Viola is a physicist, and she's working now at the MPI, Max Planck Institute for Dynamics and Self-Organization in Göttingen. And she's also a lecturer at the Göttingen University. And before that, she completed her doctorate at the Max Planck Institute for Brain Research in Frankfurt. Now, Viola's been working on, in general, she's been working on global patterns of neural activity and how local rules can engage or promote those local patterns of activity. And also, she's been working on how can we learn something about those global patterns of activity by observing just subsampling or part of those neurons. And since the outbreak of COVID, she's been using her experience and knowledge on the matter to study how to understand the spread of the COVID as a disease and how to mitigate it. And she's also been, she's been advising to politicians in Germany how to mitigate it. And we're very happy to have her here for our first talk. Will she discuss specifically COVID, but also hopefully a little bit about this its relation with her research in neuroscience. Now we're going to leave all the microphones on for everyone, so please turn your microphone off so you'll be able to ask questions if you want. We encourage questions within the talk. If someone does not feel like it or too shy, one of the students, you can write down your question in the chat, and we'll bring it to the speaker at the end. Viola, the stage is yours.
Yeah, thank you very much for the invitation. It's also a pleasure and an honor to be here, the first speaker of the seminar. So of the semester, I wish you a really good start here. Talking about COVID, I hope we can stop talking about COVID, at least the acute crisis, soon. Vaccination is over. Israel has been always a big, let's say, example to us here in Germany in many ways, but also a study example to know what to expect next in our country. So we have been looking a lot over. It's also very nice to see a number of familiar faces here in the audience. I will talk today a bit mainly about COVID. There's quite a bit more neuroscience I would like to talk to, but I've been splitting my time literally in the last 1.5 years, a third into COVID research, a third into neuroscience, a third into public outreach. And my COVID talks at the moment are just better than the neuroscience talks at the moment, but that will change. So why did I come from neuroscience to COVID? That is pretty, let's say, straightforward if you understand what we have been doing in neuroscience to some degree. So one of these really combining features has been spreading dynamics, spreading of activity in the brain, and spreading of a virus in a society has, at least in its basic mathematical properties, some similarities, as I'll point out later. Then we basically, in quote, try to fight COVID pandemic with equations. From basic research to crisis response is how I try to understand, how I try to give an idea how we went into the crisis mitigation. And then I'll take some time for the neuroscience part, which obviously my heart is closest to. Nonetheless, starting with this already classical imagery of the zebrafish larvae, we know there's activity, we know it's spreading in that brain. We know for the zebrafish larvae it's 100,000 neurons, but nonetheless we can only sample or have a glimpse at that for a number of reasons. So here it's a time-lapse video, we don't have the perfect spatial resolution, or we don't have the perfect temporal resolution. And that all makes it challenging to understand how activity and the later information runs in that system. So we started to study then a very, very simplistic model in a way that tries us to understand the backbone of spreading, and also to understand how one can estimate spreading in such a system, even if only a tiny fraction of the system is modeled. And I want you to see this as a very basic math course, maybe, the first few slides here, or introduction to a process that plays a role as a, let's say, the drosophila for spreading dynamics, no matter whether it's fake news, whether it's COVID, whether it's perturbations in a system. So let's assume, and we can go here with the original notation from Galton and Watson, it should be 1875, so almost 150 years ago. They wondered how family names spread. That's what was their motivation. They wondered why some family names die out or not. They just assumed that there is a father, and that father might have a random number of sons, and that random number of sons, each of them might again have sons, and thereby that family name might spread or not spread. Mathematically, what this is a branching process, and they back then could already show that if a father on average has less than one kid in that population, then there will be exponential decay. The family will for sure die out after a certain number of generations. If a father has on average more than one kid, we'll have exponential growth. And you know by now what exponential growth is and what this R value really is. It determines exactly whether one of these chains will spread or not. These two phases are separated by what we call criticality. For anyone of you with a background in physics, that's separating two states here, in this case, the stable from the unstable dynamics. And it has some properties, as I'll show later, that can have advantages for computation. So we were mainly interested, first of all, in basic questions of how can we get just this R value out of the data that we observe. And for the mathematicians among you, the derivations are straightforward. If you look at the equations, such a process is defined as A of t, that's the number of active units in a system at every single time, so the number of people with a certain family name, let's say. And what is it at a given time? This only depends on how many there have been before and how many offsprings each of them generated. So we sum over all of these families in the generation before and assume that each of them produced a random number of sons. And this random number can be 0, 1, 2, 4, or many. And what really only matters here for stability is the mean value. So how many children on average does such a family of that name produce? And then it is straightforward. If you take expectation values here, it's straightforward to calculate the R value. You relate the activity or the number of family names at one generation and the one at the next generation in the linear regression here. That is a consistent estimator for the R value. And what you find here is a small offset. The small offset assumes that there could be immigration. For viruses, it makes sense. Someone coming in with a plane to Israel, for example. For family names, it would be someone, a new family adopting the name just because it's so beautiful, maybe. Anyway, so that is the external input. This is something that typically in the estimation of R values, like the way it's done, at least in Germany by the authorities, is not done, but that's details. And it doesn't make a big difference as long as that value isn't too large. So we simply relate number of cases at one time point to number of cases in the next generation. Generation time is 4 days in COVID. If it's here in generation of humans, there's intricacies about it. But it's something we can do with fairly little data. However, we were inspired by neuroscience. It's applied mathematical problem, but we were inspired by neuroscience. And we wondered the following. Take the human brain. The human brain has 80 billion neurons. Now take advanced recording techniques. This is a bit older slide. And then I say, well, we can record 100,000 or maybe 1,000 neurons with really high temporal precision of millisecond resolution, where we can see I would say the generation time in neural network, we don't know it, it's variable, but it's on the order of milliseconds. Now with larger probes, we get more neurons, but we are still far from recording all the 80 billion neurons of a human brain or the 80 million neurons of a mouse brain. So we wondered, how does just looking at the tiny fraction of the system, I illustrated here in the sketch, so looking only a tiny fraction of all the neurons in the dense network, how does that infer with our inference about the entire system. And we showed in a number of studies that the subsampling, the spatial subsampling, may lead to misestimation. What we have been developing is bias-free inference. I'll not talk today, but maybe that's interesting for some of you, about bias-free inference, for example, of graph structure. That's not about spreading dynamics, but take a large graph, you only see a fraction of the nodes. How can you still infer what's the full graph structure, the degree distribution, for example? This is where we develop closed form solution. We also developed it for spreading dynamics. I'm talking about it because suddenly it became quite relevant for neuroscience. Just to tell you how severe that problem is, I would like to illustrate it here. So we have here the spreading process from before. We just assume that some of the events might not be observed. How do we still make that inference? Here are 3 different chains illustrated. Now imagine there would only be 3 recording electrodes. Then we would hardly see anything anymore from these chains. We still want to infer what is the spreading in the entire system. And if we then use that estimator that I introduced before, just relating activity at time t and in the next relevant time step, well, if we do that under subsampling for just in this case 10% of all the events, then we underestimate that R value. So it looks as if there was much less local spreading than there is in reality. And actually what we're measuring here is very closely related to the correlation. And it seems that already the correlation of activity from one step to the other is in a way biased or not representative for what we would expect for correlations in the full system. If measures as basic as the correlations are biased, then a lot of collective properties that we would infer are potentially biased. This is a side note, it's just something that many researchers anyway do, but if you then think about properties, if you try to find out about or characterize your full system, but only look at a tiny fraction of it, it's always good to check whether potentially your measure you're looking at has some subsampling bias. We overcame for this type of spreading of activity, we overcame the bias. We could generalize our estimate. We generalized it here from AT and AT plus 1 to general delta t's, and thereby we can partial out the bias. So first question would be, why is there a bias? It is because the observation becomes more noisy. If you only see a fraction of all the events, this brings in additional variance. If you bring in additional variance because of observation, you underestimate the correlation strength. So this can be overcome if we generalize to any delta t, because the sampling induced variance is in principle always the same. We don't know it because we don't know the full system size, but we can cancel it out. That's the only important part. We don't have to know it, we just cancel it out by taking a lot of these relations. This estimator then returns the control parameter R instead of, and that's where we actually started from historically, instead of a test for or against criticality. It is efficient, it's precise, it's easily applicable. It only requires knowing the number of neurons you sampled at any given time step. It does not require knowing the system size n or the number of sampled units. In fact, we need just a couple of minutes of neurons at most to then have a reliable estimate. Under ideal conditions, and with ideal, I mean really a model. I mean a model where we can control that all the neurons have roughly the same properties. There we can in principle just record a single neuron. And then from the return times at that single neuron, we can estimate what's the spreading in the entire system. So it is a powerful measure. It has been applied by a number of people. And I'll show you in the last part of the talk how we make use of it. Now, I've been talking here about branching processes, and I would like to note that this branching process is obviously not how I believe that neural activity propagates in the brain. We don't have this amount of stochasticity, and we have this very prominent integrate and fire mechanism. So this is just an example where we can derive analytically how we can estimate the spreading of activity, even if we only see a tiny fraction of the system. I can't go into that, but we showed numerically that exactly the same estimators, they also work for integrate and fire networks of excitatory and inhibitory neurons. So the same approach works, although we can't prove, although we can only do the proved analytical derivation for the branching process because of the complexity that we have as soon as we go for integrate and fire neurons. On the one hand. On the other hand, you saw that already back then when we developed the estimator, we applied it to disease spreading. That was in 2018. Here, that's our paper from 2018. There we applied actually that estimator to the spread of measles in Germany. Why measles? We knew it is probably fully sampled. So here's the estimated reproduction number. And here's the sampling probability. If fully sampled, then our estimator and the conventional estimator bring the same spreading for the measles. But if then sampling only 50%, 20%, or 1% of all measles cases, then the conventional estimator underestimated the spread, whereas ours just showed larger variance depending on the realization, which is simply because of little data. The fewer we sample, the less data there is, but it is consistent. So back in 2018, we already estimated spreading, and that is what threw us, so to say, in the middle of the COVID pandemic. So we're showing you how we have been investigating spreading dynamics and also developing a subsampling theory. I guess that you do understand that working on COVID was absolutely a natural thing for us to do. We did it already in January when the cases spread in China, end of January. I remember how proud one is as a scientist if one predicts the crossing of the mark of 1,000 infections in China kind of by the day. But we didn't really realize that it would come so quickly to Europe and that it would really change our life for years, probably. We had the models in place. I don't know how it's in Israel, but at least in Germany, I was then waiting for the people who do epidemiology of infectious disease. But actually, we don't have that in Germany. We didn't need it for the past 30 or 40 years. And therefore, this is a branch of research that had been completely abandoned within Germany. This is different in the UK and some other countries. But here, we basically had no one. And this is what suddenly made me one of the central figures in trying to predict the spread of COVID. We did a number of studies in that context, and I don't want to go into detail because I feel, I don't know how you feel, but I feel that COVID starts to be over. We might be also all a bit fed up, but I would at least give you a glimpse, first an overview about what we did, and then a glimpse about how we designed our approaches. The first thing we did very early in April already was to infer change points and the effect of interventions in the COVID-19 pandemic. So Germany had 3 very clear dialed levels of interventions in March. And beginning of April, there was sufficient data to infer the effect size associated with that. We then went more towards trying to understand how different type of interventions might help the pandemic. And we were interested quite a bit in the test trace isolate system. Why that? Because the very earliest paper out there, the very early paper, they claimed strongly, I think, that as soon as we have testing, tracing, and isolation in place, we are basically set and we can eradicate the disease more or less. But there's a lot of real world problems if one goes to test, trace, isolate, and that is something that we wanted to investigate quantitatively. We also estimated what is the progress of vaccination and how we can then lift restrictions at the pace of vaccination. I will now go into this middle part here. It is something that then does not directly have to do with the spreading process proper, but here we used compartmental models. The standard compartmental model, for everyone who has been looking into that, I think that you're familiar with that. This assumes 3 compartments: the susceptible, the infected, and the recovered. There are certain transition rates between these compartments, and what really makes the disease then exponentially growing in the beginning, that's here the reproduction rate. It means initially there's few infected, but if they then meet susceptible people, then with a certain reproduction rate, there's more and more infected that then infect more of the susceptible. And that leads exactly to that exponential growth. That's only initial. That also doesn't take into account the spatial distribution of infections. That's something maybe of interest. This here leads really to exponential growth initially, as long as there are not many recovered. If you would have instead a 2D model of people where everyone only interacts with the local neighbors, then the spread would grow linearly. It would grow with DR, so the change in your radius. like a circular wave growing. So somewhere between exponential growth initially, depending on network topology, and linear growth is what one expects given a certain R value. One can then expand that model. For example, here we explicitly then model the exposed pool, people who already carry the virus but are not infectious yet. This is important if the specific timing is plays a role. And in test trace isolate, this timing plays a role because it's very obvious. The earlier you manage to identify the contacts, and if you manage to identify them before they infect other people, then obviously it's much more efficient. How do we then set up such a model? So I think the art of COVID modeling is a bit different from what we typically do in neuroscience, where it's about principled approaches. COVID modeling here has a very much a problem-driven approach and has to deal with all the real-world challenges that we have. We try to put that in here as follows. So this would be a population of infected people, and this represents an iceberg. The iceberg has this part that is already visible. These are the people who have been tested positive. So they are ideally under isolation. And then there's the population who's not yet tested positive. They're infectious. They behave as everyone behaves day to day because they're not aware of their infection. And therefore, they are spreading the virus quite strongly. So ideally, the R value here for the tested population, the isolated population, is smaller, considerably smaller, not zero, compared to the R value that we have here. And the R value here of the hidden pool, the R value of the hidden pool, that is what is determined by our day-to-day contact behavior. This is what changes if there is a contact ban or if there is a lockdown of one or the other strength. Now, all this testing and tracing does not work perfect. One of the challenges we had, especially in the past year, was pre- and asymptomatic infections. These are hard to detect. We know that with contact tracing, a fraction of the infected people might be missed. Quarantine is not perfect. People might simply not comply with it. People who do not get tested for especially socioeconomic reasons should be considered. So if you have a strong negative impact from getting tested, maybe because you can't go to work, then then you will definitely avoid your testing. We have introduction of new infections from abroad, and overall that leads then to to limits in the effectiveness of test trace isolate. But a core feature really is that also the health authorities, they have a limited capacity. Here in Germany, they literally worked with fax paper still. That means if there was few cases, then they could work on them very quickly, maybe phone all these people within a day. But the more cases there were, the higher this pile of paper was on their table, and maybe they only contacted people 2 or 3 weeks after they had been infected. That's obviously not optimal. We included that into our model as well. The model then starts to look a bit more complicated, but in effect, it doesn't have more parameters because the parameters are quite similar. It's just distinguishing compartments for the symptomatic and asymptomatic pools. Now then the question is, we can build up such a model and have such an idea, but how does one convey or how does one formalize the results? And here I would like to formalize the results for the very basic simple SIR model. How would one formalize it there? We know that with a reproduction number R, if the reproduction number R is larger than 1, then we are in an unstable regime. If the reproduction number R is lower than 1, I told you there's exponential decay. That is true, there's exponential decay, but there's a certain chain until the exponential decay really has gone to 0. So there is an expected size for this entire chain. And if we then assume that the external influx of new infections is not 0, then we can say that the daily new infections that we expect in some equilibrium, the daily new infections N, that this is proportional to your external influx from what comes from outside, divided by 1 over minus R. This 1 over 1 minus R. So this term here, this denotes and reflects the expected chain that a single infection from abroad would cause. Here you can also see this divergence. So the closer the R value is to 1, the more the smaller this value. So the larger the expected chain that a single infected person would cause. And that is the divergence or trivial divergence that one sees here at the R value. It also says that if you manage to get your R value not to, let's say, 0.99, barely below 1, but maybe to 0.9, it makes quite a big difference here for your expected number of cases. So having a safety margin from that critical value of R equals 1 really means that locally your cases would go much more down for a certain level of new infections that you carry in. This is exactly the same sketch, but now it includes and incorporates the hidden the testing and the tracing. So what happens? The daily new infections, and here on the x-axis now is the hidden reproduction number, here from people who behave as we behave on a day-to-day number. It's the hidden one. What basically happens is that this border to instability that was at R equals 1, this now shifts by testing and by tracing to almost 2. Almost 2, we did sensitivity analysis, we talked a lot to the health authorities. This is what we got out by trying to put as realistic values as possible. What does it mean that the R value shifts to almost 2? First of all, I want to stress overall the entire system is still stable. So the R value for the full system here is still stable, but it is that here the people who inadvertently, without wanting, infect others, these people can in principle now infect 2 people instead of just 1. So there is in a way the possibility to have twice the number of contacts if the test trace isolate system is in place. However, and that's a tipping point I don't want to go into in all details here, as soon as the health authorities are not fast enough anymore, then this border to instability here, that obviously shifts here to the left, and one has, if this is crossed and behavior doesn't change, one has a growth that is faster than exponential. In terms of the physics we have, and we see a metastability, so something we would then call an interesting regime, which we can characterize. And it's between these 2 regimes that are fairly clear. On the one hand, we have mild restrictions, then the daily cases are growing over time. If we would have heavy, strong restrictions, then case numbers would go down. In this intermediate regime with moderate reductions, we will reach some equilibrium of case number, which is not 0, it is at low levels. It is determined by how much we get from the external influx, how close we are to that tipping point. But in this regime, case numbers are basically stable as long as they are not getting too high, because then one tips over to the unstable regime and runs into a growth that's faster than exponential. Well, this is sensitivity analysis. I don't want to go too much into that. To summarize that part, the undetected cases, they contribute most strongly to the spread. It's because they are not aware of carrying the disease. If now the trace isolate capacity is surpassed, and we modeled it here and saw very similar behavior in Germany, if this is surpassed potentially at this point, then the growth doesn't go on as it would go with the SEIR model, but it becomes faster than exponential. This is because the R value in the background, the effective R value of the full system goes up. So this growth really self-accelerates. And finally, the test trace isolate, if done, let's say, reasonably efficient, and if case numbers are sufficiently low, then instead of just 1, a person can infect 2 persons, and this is then compensated by the test trace isolate. That gives you one glimpse into the project that we have been doing. I must say a big thank you there also to my own group here. There have been a number of PhD and master students jointly together who have been working hard to get these projects done in the shortest possible time, which had been a crucial aspect and let's say benchmark back then in the year 2020. Another thing that we did a lot then here, because I was then caught in this political advising, and I don't know how it was in Israel, but we did not have a scientific advisory board here. So it was always individuals being asked here and there, and it was also individuals being asked to talk to the press, which is extremely time consuming, and it's also a bit stressful, especially if the debate becomes heated and polarized. To avoid having to talk as a single person, and also to broaden my perspective and scope, what I did, I brought together in 2020, I brought together dozens of scientists across disciplines from Europe, and we wrote a series of consensus papers, which were finally then published in The Lancet. Because for me, that was an important aspect. First of all, to have internal peer review about the perspectives. Second, to have the cross-disciplinary perspective. COVID is not obviously only about epidemiology and spreading, but it's a lot about everything from psychology to economy. So we had these very productive discussions that we then summarized, iterated, and then within a short time could address some of the urgent questions of the time. And the third reasons I did it is because then in public I could communicate, not just for myself, but I could communicate for and with that group jointly and alone. And that also alleviated quite a bit of the pressure on a single person. And it also helped us to bring together really the interdisciplinary perspectives, not only if one person talks to the press, but if as a group we could then talk to press. So this is roughly what I was then busy with in the past winter. Coordinating a few dozens of researchers from all over Europe was a lot of fun, but you can imagine it was also kind of a bit of a challenge. So with this, I would then like to close the COVID chapter and move on to the neuroscience part. So in neuroscience, why are we interested in branching processes? I bored you maybe with this very initial introduction into a mathematical framework that I find very elegant, but nonetheless, it is a simplification to what's going on in the brain that one may or may not do, let's say. Well, the simplification of using a branching process is for a number of reasons. And one of the reasons is that if one is interested in these critical states here, in these transitions between stable and unstable dynamics, just this balance where activity doesn't die out but doesn't become unstable, these phenomena are collective ones. So it's not only about the single neuron contribution, but it's about how they cooperate. And it has been proven, and it's known since a long time in physics, that if it's about these collective properties, then the single properties of an individual neuron, whether this is now a neuron or a stupid here branching object, this does not matter anymore for the overall collective dynamics. So that is one of the reasons why we still use branching processes for the so-called universality. Actually, here the Nobel Prize a week ago to Giorgio Parisi his work was exactly on this understanding of how the interaction of these small local units then give rise to global properties, and how these global properties how they become independent of what the single neurons do. Nonetheless, I know that I always get these questions, so I say it here. The branching process is a beautiful way to do some educational mathematical background, but then we always make sure that this also holds for integrated fire neurons and others, so that this so-called universality holds. Now, why are we interested in this critical phenomena after all? I think a number of you might have heard about this criticality hypothesis. Since maybe 30 years, people are speculating that the brain might operate at a critical state. You can call it a crazy physics perspective, but let me tell you what I think is helpful about it and what we should take also with a grain of salt. Again, starting with physics here, what happens at a critical state? This is the classic Ising model. The details are not too important, but the main aspect here is as well, either a black spin here makes all their neighbors black, or the spins are very independent, they do whatever they want. And in the middle, you find then this, at the critical transition, this collective, this large scale phenomena arising. It means also that a neuron active, if one is close to criticality, in principle can influence the activity of any other neuron via all these indirect connections. Why is it? It is because these systems become very, very susceptible, very sensitive to input or any perturbation if they approach that critical point. And this divergence, this going up of the properties, that is something that might be useful abstractly for computation. It might make such a neural network an interesting substrate. So if one compares this Ising model that has here this susceptibility going up extremely steeply, we call it divergence. So if we have this susceptibility going up, that is a sensitivity to input. And sure, I think a network should be sensitive to input. No one would doubt that. The specific heat is an aspect that also goes up and diverges at the critical point. That would be the accessible coding space. So how many type of patterns you can really realize in that network. The correlation length, so whether a neuron is correlated with others. So that also goes towards infinity at that critical point. And that could be used for long-range communication. People talking, for example, about these intrinsic timescales, about which are used in reservoir computing. This rise and this increase, the closer one is to this type of a transition. And as said, all this does not depend really on how is the detailed properties of the units interacting, but whether they manage to globally coordinate or not. How they do it is secondary to it. Now, the statement that I think has been put forward and has led to a number of confusions is that people then stated that criticality optimizes computation, really unconditionally. Criticality optimizes computation. I think you have heard that in one or the other talk, and I'm not sure whether you agreed or not. What I would like to say here is from physics, what we can say is that criticality maximizes certain processing properties. But whether you want to have these properties maximized or not, I'll show you later. This really depends on the task at hand. There are tasks that can profit from it. There are tasks that are really not profiting from this maximization, not optimization, from this maximization of processing properties. Two more slides on this origin of this criticality hypothesis. Chris Langton and Alan Turing, they managed to find a way to decompose any information processing, transfer, storage, and modification. One can measure them using information theory. So here with transfer entropy, for example. If one does that in a standard recurrent network, so this is a recurrent reservoir network, one then asks the output to memorize the past and return what has been the past input. And then ideally one even asks in a way this network to do some nonlinear computation, like combining and doing a complicated function on the past input. Then what one finds is that this network performs best if it's close to the critical point, and then one also finds that the transfer of information between pairs of neurons peaks, and also the storage of information in terms of mutual information between past and current activity, that also strongly peaks. So we do have evidence that abstract measures, we could say objective measures of information, that they clearly peak at the critical point, and that also in this type of reservoir computing systems, there is advantages of this criticality. But now I said, is it really that optimal? Because you also know that there's a number of people who argue, or rather for a disordered state, which is asynchronous or irregular. So the critical state, I said, it profits from the strong amplification. It could profit from long reverberations. No one would argue that we are in an unstable in the R value larger than 1, at least not for a long time. But there's people who could argue that we should rather be in a disordered state here, that we should minimize the correlation, because with minimizing correlation between neurons, we have minimal redundancy, we would have maximum entropy. That also would have its advantages. And quite a big part of the people working on balanced networks and this asynchronous irregular state, they wonder how can a network organize itself to a state where the correlations are minimized among the spiking. So why having a redundancy if you can avoid it for optimal compression? That's definitely not a good idea. So what we do argue after throwing our estimator to neural data of rat, of cat, of monkey, of human, and also others using our estimator, what we find is that the dynamics neither really represents what is close to critical, nor it represents really a disordered state, but something in quote in between. Why do I say in between? I mean, it still looks as if it was quite close here to that critical transition, and it's close to the critical R value of 1. I say in between because in terms of here, for example, the information transfer in the network, the correlation length, in that respect, it makes a huge difference of whether you are, let's say, at 0.9 or at 0.99, so closer or farther away from the critical point, because it really quenches how much of the information or correlations are transferred or not. It also shows that very small changes now in your effective spreading. How could you change it? You could change it, for example, via neuromodulation. Neuromodulation could do a 2, 3, 4% change in your effective excitability in the network. These small changes could bring you from a state that's closer to the disordered, so it would profit from all the advantages of this disordered state, but it could also, with neuromodulation, bring you closer to the critical state, make the system more sensitive and greatly more sensitive, just by a tiny, tiny change in this R value, so a tiny change in the effective excitability of your network. This is what we think might be a good reason for the network to be not at criticality, not below, or really far away, but to make use of the strong changes of computational properties that we have close to a critical state. If, in contrast, the system would be much farther away, then the same amount of changing your synaptic strength, for example, by a neuromodulation, would have hardly any effect on the network sensitivity or information transfer. And if you would be very, very close to the critical state, then small changes, I mean, it's a biological living system, it cannot be arbitrarily precisely tuned. It has much more to do than just tuning itself towards a critical point or not. So then if you don't keep a safety margin, then running into that unstable system, into this unstable regime might have a certain disadvantage. So this regime close to, but not yet at the critical point, might have its advantages. Sorry, I skipped it, screen between. But yeah, okay. Anyway, getting lost in my screen. We also checked whether with deep sleep or rapid eye movement sleep, this working point change, and that seemed to change. And even that seems to make sense in the following. We know that in deep sleep, we have memory consolidation. That means brain areas should work together. We have the slower sleep, which clearly also shows strong correlation. And we find that this is reflecting a state closer to the critical point, whereas rapid eye movement state, its acetylcholine is high. This rather decorrelates neural activity. And it seems to be more on the lower range of that regime where we do find neural activity. So, sorry, this one is the old notation, but this is the R value. The R value apparently is close to R equals 1, but somewhat below, and being somewhat below, just a few percent below, makes quite a bit of a difference for computation. Other people also contribute similar work, in vitro work. That's something we find seems to be fairly close to the critical point itself. Happy to go into that as well. Now, one would think, like, if that is really the case, if we should have different working points, I mean, I know there's much more to computation than just the collective dynamics, but from this collective perspective, if there's different working points, then we should see that. We should really see that in the brain we should see it in a single brain, because one brain area and its own task might profit being more away from the critical point. The other brain area might profit from being closer to that critical point. And actually, these are preliminary results that we obtained with colleagues from the US, with Nick Dodson and Charlie Gray. They recorded neural activity from macaque monkey with extracellular electrodes from many brain areas, more than 40 brain areas in parallel. What do we find? So here's now the branching parameter R, color-coded. These are the visual areas, and we find the visual areas to be rather far away from the critical point, if we may say so. So they seem to have a low branching parameter. Low branching means they receive the activity, they receive the input, they also can forward it, obviously, but that input also decays. So we have the, in quote, advantage of fast forgetting there. In contrast, here the frontal areas, they are closer to the critical point. And that might be because they are integrating information over a longer time, and their being closer to the critical point might really help them to integrate information over a longer time and also over multiple modalities. I think I can give you then, concluding sentence for my slide here is that this perspective of criticality might tell you something about the sensitivity of the network and its own working point, and how basically, maybe over evolutionary terms, each of the different brain area found a slightly different working point depending on the computational needs that you have in a given brain area. Now, one could ask, can we really reproduce that in a model? And how does the network tune itself there? I think I have a bit too many slides for this entire endeavor. I wonder where to continue at that point. Let me maybe skip that first part. The first part here basically shows that in a neuromorphic chip, we can tune the chip towards and away from criticality. Here it's away from criticality. We give it different tasks of different difficulty. And then if the task is quite difficult, you have to integrate over 25 bits, then it is advantageous to be close to the critical point. If the task is fairly simple, then it's better to be farther away from a critical point. This is a chip with integrate and fire neurons. And the other project to jump over there is on the question, how do we bring the network towards or away from the critical point? And that is on homostatic plasticity. And homostatic plasticity might really be the mechanism that makes a difference whether a system becomes closer or farther from a critical point. So there, homostatic plasticity, most of you might know, really has the property to bring a network, or to bring every single neuron close to a certain target rate R. And if that neuron has a target rate that has its own rate lower than the target rate, then the excitatory coupling is cranked up until it reaches target and vice versa. If one puts such a homostatic learning rule, which is basically can be implemented completely locally into a network, then we find that it tunes the network again towards or away from criticality, depending on the external input. Let me show you how that works. So the homeostasis has a change in synaptic strength that depends, that is completely independent of any memory process. We can implement it as a small increase in the synaptic strength whenever the neuron is not spiking, a gradual decrease whenever it's spiking, and implemented on a very slow time scale. Then we have a learning rule that only requires a local information, doesn't require memorization, but it can in principle bring every single neuron to its own target rate R. If you implement it with a local topology, then what we find is the following. We find that if the input is strong, then the networks show rather continuous activity close to what we find in vivo. If the input is very, very weak, then these networks show fairly bursty activity that resembles what we find in vitro. So one of explanation for what I have been finding a very puzzling question, one explanation would be the following, that in vitro, whenever you do an in vitro experiment, you find this very characteristic burst. It might be because homeostasis without any input brings the network to this bursty states. In contrast, if you think about the in vivo system where every single brain area is embedded in the entire brain and there's continuous input, then this would self-organize the network to a state that's much closer to the 0.98 that I showed you before. So under homostatic plasticity, the input strength would become the control parameter that determines whether the overall collective dynamics is more bursty, close to a critical state, or more continuous, farther away from the critical point. And that's a very elegant way to control dynamics, and it could explain the differences between the emergence of these differences of input strength that might explain the emergence of the bursts in vitro. with this tour de force, first from spreading dynamics to COVID, to self-regulation of activity neural networks. I hope you apologize that I squeezed in that much into a single talk. But I would like to really thank my group here in Göttingen, who's been working on both of it in parallel, the COVID and the neural networking activity. Thank you very much.
Thank you, Viola, for this wonderful talk. We have a few questions we have a question on the chat. It's a bit long. I'll try to kind of rephrase it. And so you were talking about the phase transitions in a highly disordered system, or in a two-dimensional spatial mode in case of the Ising model. So the question was whether you expect a good fit with real data. I'm not sure if they mean here neurons or in the COVID case, in the spatial model, when you would just choose the right dimension for the connectivity instead of two-dimensional or an SK model, somewhere in between.
So I think first for COVID, it seems to have the self-regulation mechanisms that we always go to R equals 1. If case numbers are too low, then we increase it a bit. If case numbers are growing too quickly, so R value is too high, then we tend to decrease it. So there seems to be some homeostasis working on the R value. In terms of whether we can do any of that in COVID, I think not at all, because these parameters and the behavior of people and the boundary conditions are just changing way too quickly, I think, to do meaningful analysis. So we don't really have anything close to a sufficiently stationary period of time there. In terms of the neural data, it's really the main challenge that we have, that, well, a neuron is connected to a few hundred or more other neurons, and these neurons can be somewhere. So if we record now 2 neurons, we have no idea what is their topological distance. And that makes many of the spatial aspects of the analysis very difficult to apply. One way around there, and we are doing that, and also another group is doing that, is Dahmen et al. In the group of Moritz Helias. They look at the distribution of covariances. So they say, well, there is some space. We don't know it exactly. We don't know how close 2 neurons might be, but we have some expectation about how the covariance matrix should look like. And this is a way to use space without knowing the topology to assess this potential spreading dynamics.
Okay, more question. I have a question in the meantime. So you were talking about a sort of a phase transition there, but it seemed like there are 2 phase transitions. One would be about being the effective excitability just on the verge, which we can happen in a completely ordered state, and the other one is on the verge of replica symmetry breaking, which between the ordered and disordered state. And so both of them would show high susceptibility or the verge of susceptibility, but can you separate between them in your data here? I mean,
yeah, it's not only a question about separating them. Potentially, at least there are multi-critical transitions where you could be at or close to a critical point for one of the transitions, but not for the other one. I've been concentrating mainly on this stability-instability transition because I have the impression we can have a handle at that, despite all its simplifications that we have in the derivation. So I've not looked too much into the others yet, so I'm sorry, I can't give a more.
So this picture when you have this Ising model and different domains and where you'd expect crackling noise, so that's not the type of.
I think we don't get a handle at space in the neural networks. At least I don't really believe that we have a handle at space. I mean, even if we have a, let's say, 2D electrode array or a calcium imaging like data, what we see there in space still reflects a bit the underlying topology, but it's not. Yeah, I think I would like to know what is really the true underlying topology before one says anything about that.
We can still see that in an SK model when there's no topology to the space, right? In a completely random connectivity all to all.
Yeah, indeed. Yeah, I mean, in that sense, you can go for this cluster sizes, avalanche sizes, which has been done a lot. And they show the scale-free patterns. Yeah, that's something we can do. Not space. If you really ignore the spatial topology, and if it's just about, we can then almost summarize it as population activity. And yes, we then have properties of crackling noise and this avalanche type of activity. Yeah, in that sense, yes, absolutely.
Yeah, I could talk more about it, but we are kind of on stoppage time. So if there are any more questions from people here or at home, and if not, then we'll thank Viola. And next week we have another Zoom talk. So hoping to see everyone virtually next week. And thank you very much. Thank you, Viola, for a great talk.